All right, so this is the last section of Unit 6. We're taking a look at solving logs and exponents. In order to do this, all right, we first need to know some properties for solving exponential equations. This first property of equality for exponential equations says if b is a positive number other than 1, then b raised to the x power equals b raised to the y power means that x is equal to y. So how is that helpful for us? It's helpful because as long as the bases are the same, we can just drop the bases and say that x is equal to y. So let's take a look at this first example. It says number 1, 4 raised to the 3x is equal to 8 raised to the x plus 1. The hint here says make the same base. 4 and 8 are not the same base, but both of these numbers can be made by taking 2 and raising it to a power. So this first one, 4, is the same as 2 squared. So we replace 4 with 2 squared, and we say that's getting raised to the 3x. That's going to be equal to 8 is really 2 cubed, so that's 2 cubed, and then that is getting raised to the x plus 1. So this 8 is 2 cubed, this 4 is 2 squared. Now we can take this and use our exponent rule, raising a power to a power. That would be 2 to the 6x is equal to, and then we distribute this 3 to the x and the 1, 2 to the 3x plus 3. Now, just like the property above, we have the same base, right? The base here is 2, the base here is 2. So then we can drop the bases and then just say that 6x is equal to 3x plus 3. Now we have an equation we can solve. So we subtract 3x from both sides to get 3x equals 3. Divide both sides by 3 to get x is equal to 1. And that's how you're going to do a question where you need to make the same base. All right, let's throw another example out there. Example number 2. It says 25 to the x minus 1 is equal to 125 to the 4x. 25 and 125 are both powers of 5, right? So 25 is really just 5 squared, so that's 5 squared raised to the x minus 1. And 125 is 5 cubed, so that's 5 cubed raised to the 4x. We use our power property rule, power raised to a power, and we can say 5 to the 2x minus 2 is equal to 5 to the 12x, because we multiply. And now we have just a base of 5 in both of these, so we can drop the base, and we can just say that 2x minus 2 is equal to 12x. You subtract 2x from both sides to get negative 2 is equal to 10x. Divide both sides by 10 to get negative 1/5 is equal to x. Just like that. All right. Next one up. Number 3, we have 36x minus 9 is equal to 6 to the 2x. And the case on the left here, we can make a 6 from 36. That's really just 6 squared raised to the x minus 9 is equal to 6 to the 2x. We're going to distribute this 2 here to get 6 to the 2x minus 18 is equal to 6 to the 2x. Now we have just 6's as the base, so we can get rid of the bases and say 2x minus 18 is equal to 2x. If you subtract 2x from both sides, you get negative 18 is equal to 0. This is not a true statement, so we get a no solution answer here. If it would have been 0 equals 0, then we could have said all real numbers. But in this case, negative 18 does not equal 0, so we say no solution. All right. Next, to solve, we're going to use logs or natural logs. So in this first method that I'm going to show you, we'll call this method number 1, I'm going to use natural logs. And it actually goes pretty similar either way. I actually prefer natural logs because they work all the time no matter what, and you don't have to do change of base formula with natural logs, which is kind of nice. So Solving with natural logs. In order to do this, you have to isolate the exponent. Our exponent is here on the 10, so in order to isolate that, we subtract 3 from both sides. That's going to give us 10 to the 2x is equal to 5. Now we have an exponent isolated. At this point, this is when you're going to take the log, in this case, the natural log of both sides. So we natural log here, and we natural log here. And that's not multiply by the natural log. It's physically putting each side inside of a natural log. The reason we do this is because we can now use our properties of logs. So we can take this 2x, so we can drop it to the bottom. This is going to give us 2x multiplied by the natural log of 10 is equal to the natural log of 5. To finish solving here, you divide by 2 times the natural log of 10. That would get rid of the 2 here, and then the natural log of 10 here, and then you do that to the other side. 2 natural log of 10. All right, and then what does this value give us? It gives us that x is equal to the natural log of 5 over 2 times the natural log of 10, which is approximately 0.349. And we're good with just 3 decimal spots on these, all right? I do use the approximate squiggles because we are, for the most part, when we use natural log or log to solve, going to round our answer, so it's always approximate, right? So let's kind of review the steps here. The first step that we took was we had to isolate the exponent. Second step that we took was we natural log both sides. Not both sides, both sides. And then the third step that we took was just solving for x. So it's really just 3 steps that we took there. I guess unless you need to include this x or log property that we also threw in there. All right. So let's do method number 2 down here. We're going to use just logs. All right. This is method number 2. And either of these ways are great methods to solve. Again, I prefer natural log the most just because you'll see you don't have to use change of base formula, but when you use logs, you do. So just like the last one, the first step is to always isolate. So we have to isolate these exponents by subtracting 4 from each side. That gives us 7, 2x minus 3. 21 minus 4 gives us 17. And now we have the exponents isolated. If we're using logs, we need to take the log with the same base as the exponent. So we're going to go log base 7 here, and then log base 7 of the other side as well. Notice I always put them in parentheses because, again, we're taking the log of both sides. We're not multiplying by log or something like that. So you take the log with the base of the same as the exponent because we learned the other day that this log and the base cancel. And so we're just left with 2x minus 3, and that's going to be equal to log base 7 of 17. At this point, you could get the decimal here, or you could just keep it as it is and keep going and plug it all into your calculator at the very end. But let's just say, let's just grab the decimal right now. So this is going to be 2x minus 3 is equal to log base 7 of 17. If we want the decimal here, that decimal is going to be 1.456. And how you get that is your change of base, which would be log of 17 divided by log of 7. All right. And that is going to be our change of base formula that takes us from here into here. So that's equal to 2x minus 3. You add 3 to both sides to get you 2x is equal to 4.456. Divide both sides by 2 to get x is approximately 2.228. And again, 3 decimal spots is good for any questions like that. So now it's really up to you. You can use logs, you can use natural logs. Whenever the base is e, though, you definitely want to use your natural log here. That just makes the most common sense. So Exponent already is isolated. We can skip that step. Now we're just going to take the natural log of both sides here. So natural log of e to the negative x. Natural log and e cancel to give us negative x is equal to the natural log of 6. Type in the natural log of 6, you get 1.792 approximately. So negative x is equal to 1.792. Divide both sides by negative 1 to get x is approximately negative 1.792. All right. And then our last example down here. Again, prefer natural logs over everything because you can always use them with e. And I showed you that you can use them even when the base is like 10 or the base is 7, whatever. All right, so we're going to use natural logs here again. So isolate the exponent, subtract 9, gives us negative 5e to the negative x is equal to negative 3. Divide both sides by negative 5 to isolate that exponent. So that's e to the negative x is equal to 3/5. Now we can take the natural log of both sides. So we take natural log of here, natural log of 3/5, which that is going to give us negative x is equal to the natural log of 3/5. Okay, then we just divide by negative 1 on both sides to get x is equal to the negative natural log of 3/5. And then our approximate value there is approximately 0.511. Okay, so that is solving exponents. Now let's take a look at solving logarithmic equations. Exponents and logs are related, so it only makes sense that the property of equality for logarithmic equations is super similar to the property of equality for exponents. If b is a positive number other than 1, then if you have the log base b of x is equal to the log base b of y, this means that x is equal to y. So that's just like our exponent equation, right? We said b raised to the x equals b raised to the y. Well, again, if the base of the log is the same, what's inside of the log has to also be equal. So the first method that I'm going to show you for solving logs is this method called exponentiating, which we've already talked about once when we were solving for inverses, right? So let's exponentiate. In order to exponentiate, you have to isolate the log. In this case, log is already isolated. So then we're going to exponentiate both sides with 3. And what that did, remember 3 canceled with the log, and you were left with 5x minus 1. On the other side, we have 3 squared, so that's going to be equals 9. Now we're just solving for x. Add 1 to both sides, so that gives us 5x is equal to 10. Divide both sides by 5 to get x is equal to 2. All right. It's always good to double check your answers here. So if you just plug this in real quick, log base 3 of 5 times 2 minus 1. That's going to be log base 3 of 10 minus 1, which is log base 3 of 9. Is the log base 3 of 9 equal to 2? We take 3, we square it, that's 2 is equal to 2. So we're good. Okay, let's exponentiate again for this second question, right? But our first step, we have to isolate the log. So we're going to divide 16 by both sides. That gives us the natural log of x is equal to 1.875. Now we're going to exponentiate. The base on the natural log is e, so we exponentiate with e on both sides. E and the natural log cancel to give us x is equal to e to the 1.875. If you plug that into your calculator, that would give you e is approximately 6.521. All right, next up, here's where we're going to use our property, this property of equality for logarithmic expressions. For number 9, there's just one log on each side. They both have base e. That tells us that the insides of these are equal to each other. Right, so 2x plus 5 is equal to 4x minus 1. And now we can just solve. So you could subtract 2x from both sides. I like that. So 2x plus 1 is equal to 5. Subtract 1 to give us 2x is equal to 4. Divide each side by 2 to get x is equal to 2. All right. And you can always check this one, right? You plug this, you say natural log 4 times 2 plus 1. Is that equal to the natural log of 2 times 2 plus 5? So that's going to be natural log of 8 plus 1, and this is natural log of 4 plus 5. Those are both 9, so they check out. All right. Another one where we can set equal to each other, right? So this is log base 10, this is log base 10. So we can just get rid of the logs and say 5 minus 3x is equal to 4x minus 9. If that's confusing to you, right, the log is isolated, so exponentiate both sides with 10. What happens? 10 cancels with log, 10 cancels with log, and then you're just left with the equations. Here we're going to solve. We add 3x to both sides. That's going to give us 5 is equal to 7x minus 9. Add 9 to both sides. So that's 14 is equal to 7x. Divide both sides by 7 to get x is equal to 2. All right, let's check this answer here. So we're going to say the log of 5 minus 3 times 2. Is that equal to the log of 4x minus 9? Oops, sorry. 4 times 2 minus 9. Running out of space here. So that's log of 5 minus 3 times 2. Is that equal to the log of 4 times 2 minus 9? So that's the log of 5 minus 6, which is the log of negative 1. This should raise a siren right here because negative 1 is inside of a log. All right, let's think about our log graph. It looks like this. Log graphs never go negative, so we physically cannot plug a negative into a log. The other reason that happens is because if you think about it, it's asking you, what do I raise 10 to in order to get out negative 1? It's not physically possible to raise 10 to a power and get out negative 1. So right here, we can stop and say that there is no solution because the only solution we got is an extraneous solution. All right, so that's number 10. And then lastly, on the example side here, we have number 11. It says use properties to make one log, then exponentiate both sides. So we have our properties here. We can combine these to make one log. We learned the other day that plus is really just multiplication when combining logs. So this is log 5x times x minus 1 is equal to 2. From here, we can say this is the log of 5x squared minus 5x is equal to 2. And now we can we can exponentiate both sides with 10, right? Because 10 is the common log base. So we exponentiate both sides with 10. Log and 10 cancel to give us 5x squared minus 5x is equal to 100. And then we have a quadratic. So in order to solve a quadratic, we have to set it equal to 0. So this is 5x squared minus 5x minus 100 is equal to 0. And one thing that's kind of nice about this is that we can divide all of these by 5. So that's going to give us x squared minus x minus 20 is equal to 0. And that should factor pretty easily. We have x minus 5, x plus 4 is equal to 0. So then our two possible solutions are x equals 5 and x equals negative 4. So let's think about real quick though, right? Can we plug negative 4 into here? If we plugged negative 4 into either of these logs, they would both become negative, right? Log of 5 times negative 4, that's log of negative 20, so that doesn't work. And then the other one is log negative 4 minus 1, which is the log of negative 5, also doesn't work, right? So negative 4, not a solution that works. I promise you 5 does. If you check it and plug it in, it would work. So that is all of the different solving things that you can take a look at. This next part is all about finding the mistakes, circle it in the problem, and then it says correctly do the following problems. Let's see, there's 6 of them here. I'm going to just have you guys try these ones on your own. The answer key is on Canvas. These are awesome questions to check your understanding for how to do these types of questions. So if you have questions on them, please let me know. I would be happy to help you. Just message me on Canvas. I hope you guys have a great day.